All right, this set of notes is about the basics of understanding energy, especially in the context of chemistry. As always, please either make your own set of Cornell notes or use the Cornell notes that were provided for you. So the biggest thing about this is once you get into the textbook, you're going to find out that there's a whole bunch of equations, and we're even going to have a whole bunch of equations here today. But the biggest thing for you to focus on is concepts, not the equations and the calculations that go with them. You'll end up with equation overload if you try to focus on the equations. All right, so big ideas then for today are to understand what is energy and to how does energy apply in chemical systems. So we'll start out with a simple definition of energy. Energy is the ability to do work or transfer heat. I like this other definition a little bit better. It's the ability to create change. So if something has the ability to create change, it has energy. So for example, if you think about the sun, okay, the sun has the ability to transfer energy and make things grow. That's creating change. So it has energy. So energy, again, is the ability to do work or transfer heat, or in other words, create change. If we cause something with mass to move, we call that work. Cause the temperature of an object to rise, we call that heat. And we'll come back and give those a little bit more time in a few slides. In terms of energy and measuring energy, this SI energy unit is the joule. Okay, a joule is equal to a kilogram meter second squared per meter squared per second squared. Older SI unit that we sometimes see in use, like in foods, is the calorie. And just here's a conversion for you: 1 calorie equals 4.8 or 184 joules. When we talk about energy in terms of chemical systems, one thing that's going to be important for us is to understand or define what the system is and what the surroundings are. In terms of chemistry, the system includes the molecules we want to study. So if this is our object or our area over here that we're looking at, in this particular case, the system would be the molecules that we want to study, the oxygen and the hydrogen molecules. Okay? The surroundings here are everything else. So the piston, the cylinder, and even the air that's outside. That's the surroundings. We can define the system and the surroundings however we want. It just needs to be clear what we're talking about. All right, so getting back to energy, some things that are important for us to understand about energy. Yep. Energy is the ability to create change. And in the universe, there's the first law of thermodynamics, which basically says that energy is neither created nor destroyed. We can store it in different ways, we can transfer it between objects, but we cannot get rid of it or create it. In other words, the total energy of the universe is a constant. If a system loses energy, the surroundings have to gain it, and vice versa. Okay. Right. So if it can't be gained or lost, what can we do, or how can we talk about energy? Well, we can talk about how energy is stored. Okay, a few different ways that are important in chemistry. One is kinetic energy. Okay, kinetic energy is the energy an object possesses by virtue of its motion. For example, a bicycle in motion. It has the ability to create change. If it runs into something, there's going to be change that happens as a result of that. It is able to change its position. So again, it can create change. Kinetic energy depends upon mass and velocity. And so as a result of that, it works for particles too, because as we said, particles have mass and they're always moving. And so as a result of that, particles can have kinetic energy. The other main way that energy is stored is through potential energy. This is the energy that an object possesses because of its position or what it's made of. Okay? For us, the most important potential energy in molecules is electrostatic potential energy, EEL, which is governed by Coulomb's law. In other words, the charges that exist on different particles and the potential energy that results from them either repelling each other or attracting each other. The other thing we can do with energy besides storing it is convert it or transfer it. So energy can be converted from one type to another or transferred from one object to another. For example, cyclists here, when they're at the top of a hill, they're not moving, so their kinetic energy is low or zero. Okay? and their potential energy is high. Why? Well, because they're on top of a hill, and so if they get up on this bike, they're going to start going down, so they have the ability, lots of ability to create change there. Okay? As they start going down the hill, their motion gets faster, so their KE is increasing, but their height above the ground is less, so their potential energy is getting smaller. So as she coasts down the hill, her potential energy is converted to kinetic energy. At the bottom, all the potential energy she had at the top of the hill is now kinetic energy, minus some that's lost due to friction along the way into the road. All right, so if energy is transferred or converted, how do we do that? Well, two ways that we're going to talk about here. One way that we can transfer energy is through work, okay? And work is simply the energy that's used to move an object over some distance. It's equal mathematically to the force times the distance over which the force is exerted. That's what we think about when we think about work. In terms of chemistry, the work that happens in chemistry is typically work done by a gas pushing on its surroundings. Right? And so as a result of that, if we wanted to measure work being done by chemical systems, we can't do that, but we have to think about that work being done in a vessel that's been fitted with a piston where we can measure how much that piston goes up and down, okay? And at that point, the work is going to be equal to the pressure in the system times how much the volume changes. Okay, so if I boil, or if I have a reaction here that's going on and I add some zinc into the hydrochloric acid, it's going to start producing gas. That gas will go ahead and push this cylinder up, and whatever the pressure is in this vessel that's kept constant by the piston going up and down, that pressure times the volume change is going to give me the amount of work that's being done by this chemical reaction. The other way to transfer energy is through heat. Okay? That heat is abbreviated as Q, which is also the same as our abbreviation for charge, so we got to kind of keep those separate in our head, which kind of Q we're talking about. And in this particular case, when we talk about heat, heat is going to always go from warmer objects to cooler objects. So we transfer heat from warmer objects to cooler objects. We give certain names to those. So when heat is absorbed by the system from the surroundings, so if the surrounding is warmer and the system brings that heat in, we refer to this as being endothermic. When heat is released by the system into the surroundings, that means it's giving off heat, we refer to that as exothermic. And I always remember this because therm means heat. Exo, I think about exiting. So heat is exiting in an exothermic reaction. It's being released. All right, so those are the basic things we need to understand about energy in order to be able to apply them to chemical systems. So in a chemical system, the kind of energy that often comes into play is what we call internal energy. Okay? This is the sum of all of the kinetic and potential energies of the components of the system. So it's the sum of all the energy that's being stored by the particles moving around, as well as the energy being stored by the bonds and the things holding the particles together. Okay? We call that internal energy E. Now, the thing about internal energy is that's really hard to measure, for us to measure the motion of the particles as well as the energy stored in the bonds that are holding them together. So we usually have no way of knowing that internal energy. It's just too complex of a problem to solve. So to get around that, we do find that we can measure changes in energy. Energy is called a state function, which simply means that it doesn't matter. Any changes in it doesn't matter the path by which the system achieves that state. So that means it only depends upon what was the initial energy and what was the final energy. So we can go ahead and calculate delta E. And we do. Okay, by definition, it is the change, the energy at the end of the system minus the initial energy of the system. Okay, so for example, over here, imagine that we're turning hydrogen gas and oxygen gas into water. What we see is that the initial state of those has a higher energy the end state, the liquid water, has a lower energy. So in the process of changing from hydrogen and oxygen into water, you get an energy change that is negative. And that means that the energy is released from the system to its surroundings. So sort of summarizing, if delta E, if the change in internal energy is greater than 0 or positive, the final energy is greater than the initial energy. That means that what's happening is the system is absorbing energy from its surroundings. That's where that energy is coming from to make the final energy greater than the initial energy. Likewise, if the change in energy is less than 0, then the internal energy final is less than the internal energy initial, which means that that extra energy got released into the surroundings. Okay. And so just like any other energy transfer, when energy is exchanged between a chemical system and its surroundings, it is exchanged either as heat or work. So therefore, we can set up an equation that says the change in energy in a system is equal to the heat transferred plus the work done. So at this point, it's worth a moment to actually look at what the signs on those different things, heat and work and energy, mean. So if we're talking about heat, a positive sign on heat means that the system is gaining heat. It's bringing in heat from the surroundings. A negative sign means it's losing heat to its surroundings. So again, endothermic, exothermic, right? For work, a positive sign means that work is being done on the system. Okay, so something is moving from something external on the system. A negative sign means that work is being done by the system. In other words, the system is doing some kind of work, like moving a piston. Okay, and overall then, delta E, the change in energy, positive means that there's a net gain of energy by the system. Okay. In other words, energy is absorbed, or a net loss, meaning energy is released. All right, so that's energy, okay? But in chemistry, most of the processes that we study are done at a constant pressure, okay? And so at a constant pressure, is in that situation where you have that and the work that's being done is pressure volume work, like with a piston, we can account for the heat flow during the process by measuring enthalpy. So enthalpy is sort of going to tell us that heat flow. Okay? Let me show you how that works. So enthalpy is defined as the internal energy plus the product of the pressure and the volume. That again isn't very useful because as we said before, internal energy itself is very difficult to calculate. So instead, the more useful thing to think about with enthalpy is the change in enthalpy. Okay. So if we figure that out, we can see that the change in enthalpy equals the change in internal energy plus the pressure, which is being kept constant, times the change in volume. Since, as we established earlier in this lecture, energy, the change in energy is equal to heat plus work, and we know that work equals, this kind of system, equals the pressure volume work, negative P delta V, we can substitute these into the enthalpy expression. Okay, so E becomes Q plus W, P minus V becomes W, and so in this particular case, we end up with that the enthalpy is equal to the heat. So lots and lots of math here. If you didn't follow any of it, this is the takeaway. That at a constant pressure, the change in enthalpy in a system is the same as the heat or gained or lost. Okay. All right. Thus, a process is endothermic when delta H is positive, and a process is exothermic when delta H is negative. All right, so that was a lot. So what I would like you to do on your left side for this particular set of notes is to go ahead and make a concept map about delta E, W, F, D, Q, P, delta V, and delta H, okay? If you don't know what I'm talking about in terms of a concept map, I've linked a very short video that explains what I want you to do for that. Once you are done making your concept map, I just want you to take it to somebody, a parent, a guardian, your dog, something, or in other words, and I want you just to talk them through your concept map. How are the things, so they can see how things are related, etc. It's not important that they understand it fully, but it's more important that you can get to a point where you sort of understand what you're talking about. That's it. See you soon.